Hello students, you've made it to OS 5. That is a tremendous accomplishment, so give yourselves a pat on the back. You're doing great. Let's look at a couple of these solutions. Number one, I have to admit, that was kind of a little bit of a softball. If you didn't have too much trouble with that one, nice job, you're getting better at these. We're taking these two molecules and making them into this one. Again, if we think about our last step, if we're forming an ether and there's no other functional groups, then perhaps our last step looks something like this. We got 4 carbons and 3 carbons. We don't particularly know, is this one the alcohol and that one the halogen or vice versa? It doesn't particularly matter. We'll see that this, if you play around with it, you'll see that this one is slightly easier. So our last step is probably our good buddy Williamson ether synthesis with, let's use some sodium this time, sodium or potassium, not sodium plus. Sodium plus is the product. This is sodium metal, just Na. With those, we'll make that. So that's our last step. And so now the question is there any way we can make a 4-carbon compound into this and a 3-carbon buddy into that? And the answer is yes. Actually not too challenging. We'll do the 4-carbon one first. We need to get rid of this double bond. So that suggests some H2 and an appropriate catalyst like platinum and palladium. That of course is MEa. So that will get rid of that one. Now we just have to do some reduction, right? The powerful type, lithium aluminum hydride. This is some powerful reduction. And pow! We're forming some water and some other inorganic stuff that we don't care about. Wow, that wasn't too hard, right? And now we just have to take this and bring it here. We can do that in one step, right? We know it's an alkene, that's the double bond is being taken away, so we know it's addition. And we want the bromine on the outside end, on the primary position, so we're gonna do a little HBr with our good buddy benzoyl peroxide. That is some anti-MEa. And then step 4 is Williamson ether synthesis, and we're done. Nice job. All right, let's look at number 2. Number 2 actually looks pretty simple too, but number 2 is a little bit gnarly if you want some really high yield, right? If you don't want to sort of like mess around, if you want a really clean reaction, this one requires some nuance. It's actually not too hard if you don't care so much about yield, or you don't want a reaction that's totally clean, then it's a little bit easier. But let me show you what I think is one of the better ways to do this. Again, retrosynthesis is your buddy. Our product is an ester, no other functional groups. That implies to me that the last step is looking something like this. Alcohol, and the right side is going to be the carboxylic acid side. Remember, esters are asymmetrical in that way. So here's my last step. In the presence of, if you want to write H plus or H2SO4, same difference. Fischer esterification. Fischer esterification, our good buddy. So that's our last step. So now we just have to figure out how to take this and make it into here. Doesn't seem too hard, right? We have a 1-carbon side and a 2-carbon side, so we just have to break these pieces apart and reassemble them into this. Oh my goodness, did I have... It's that counting thing, right? Counting. If there's only 2 carbons here, it's a lot easier if there's only 2 carbons here. Sorry about that. All right, so we have a 1-carbon side and a 2-carbon side. There we are. The trick for this is, if you start out with this reaction just by busting apart this ether, and that's your very first step, with something like HBr or HCl, that's also going to react with this piece over here, right? So if you were just to say, like, I'm just going to react this with HCl. Now you've got something like this. What is the issue with this bit? If we're using this to try to make this, notice that in the product, we only have a functional group on one side. In the reactant, we have a functional group on both sides. And not only that, it's the same functional group. Right, so we're going to have to do a little bit like add half of something and make half of those go away, or hope that only half of it reacts. So that's the part that isn't totally clean. Okay, so you can actually get a little bit better, cleaner reaction if you don't break the ether apart in the first step, which means you need to do something with this in the first step. So there's a couple of different options here. But I'm going to go ahead and add some base. Remember that ethers are vulnerable to acid. They break apart in acid, but they're stable in base. If you add OH minus, oops, wait, hold on, I did that already. We already have that here. So I'm going to go ahead and use a, sorry about that. I'm going to go ahead and use a protecting group. I got a little ahead of myself. I'm going to go ahead and convert this into the acid. So I'm going to do myself some powerful oxidation with dichromate and acid. I know I want this to be an acid group anyway. So now I'm going to get this. And if you use sulfuric acid, the sulfuric acid, because it doesn't have an associated nucleophile, will not damage this. Remember, ethers do not get oxidized or reduced, so I'm okay with that. Now I can take this apart, right? So now you can add something like HBr or HCl if you prefer. This is that ether decomposition. Now you're going to get this and this. And now we're getting a lot closer to this. When I have this and I want to take this, I want to get rid of that chlorine, and it's in the primary position. Oftentimes when you're eliminating halogens, you're using E2, but you can't do elimination, you can't do E2 if it's primary. Luckily, we remember that other way that you can eliminate things, Grignard. Right, so we're going to add magnesium in the presence of ether, and that will give us this, MgCl. And then second step, we're going to add water. Bam, and that will take that off. I'm doing it again, I have too many carbons. There we go. Awesome. So that will take that off. So this is ready, and this is almost ready too, right? We'll take this small molecule, and we'll add OH minus, and do a little SN2. And now we're ready for our last step, our fifth step, to do some Fischer esterification. All right? I think that, if I counted my carbons correctly, is one of the better, cleaner ways to do this reaction. There might be others.